Hi everybody, today we're going to talk about graphs of logarithmic functions. It's important to remember that logarithms are inverses of exponential functions. Remember, when the point xy is on the graph of f of x, we have the point yx on the graph of f inverse of x. Let's use f of x equals 2 to the x as an example. On the graph, we have the points -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. That means the inverse will have the points 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. When we connect the dots, we get a graph that looks like this. Notice the domain of the log base 2 of x is 0 to infinity. We have a vertical asymptote at the line x equals 0. Our range is -infinity to infinity. What we see here is the domain and range of exponential and logarithmic functions are exactly opposite. Exponentials have a domain of -infinity to infinity, which is our range of a log. The range of an exponential is 0 to infinity, which is the domain of our log. Notice we also have horizontal asymptotes for exponential functions and vertical asymptotes for logarithmic functions. As a recap, the properties of f of x equals the log base b of x are that we have a domain of 0 to infinity, a range of -infinity to infinity, a vertical asymptote at x equals 0. The graph will be strictly increasing if the base is greater than 1. It will be strictly decreasing when the base is between 0 and 1. We'll have an x-intercept at 1, 0. The function will be 1 to 1, and we'll have a key point at b1, which will help us graph our function. So let's go through a bunch of examples. We'll start with f of x equals the log base 3 of x, and we'll include the domain, range, and asymptote. We know the domain is 0 to infinity, which says we have an asymptote at the line x equals 0. Like before, we'll put in our asymptote as a dashed line. We said we'll have an x-intercept at the point 1, 0, and then we have a key point at 3, 1. If you want to put in additional points, I encourage you to use powers of the base. In this case, I used an x value of 9, which is equal to 3 squared. That gives me the point 3, 2. We connect the dots to get a nice increasing curve that shows us our range of -infinity to infinity. If we switch the base to a number between 0 and 1, we'll still have the same domain of 0 to infinity. We'll still have an asymptote at x equals 0 that we'll put in with the dashed line. Our x-intercept will remain at 1, 0, and our key point will be 1/4, 1. This gets a little harder to draw because the numbers are so close together. It's often helpful to put in one more point when you have a base between 0 and 1. I'll use the number 4, thinking 4 to the -1 is 1/4 gives me the point 4, -1. Again, we'll connect the dots and we'll see that this time our graph is decreasing. We still have a range of -infinity to infinity, but it feels like our graph flipped over the x-axis. To help us see how the graph of a logarithm changes when we change the base, I'm going to draw two different logs. I'm going to draw the log base 3 of x and the log base 8 of x. They are both going to go through the point 1, 0. Then, log base 3 of x will have the key point at 3, 1. Log base 8 of x will have a key point at 8, 1. As we start drawing in the graph, we'll see they're both increasing to the point 1, 0. Once I cross the intercept, I can see the log base 3 of x is slightly above the log base 8 of x. This is the higher the base, the slower the curve. Graphs of transformations will be similar to transformations we've done for other functions. We'll have horizontal, vertical, stretching, shrinking, and reflection. Let's start with the log base 2 of x and look at how we can transform that into the log base 2 of x minus 3. I've already graphed the log base 2 of x. You can see I have a vertical asymptote at the line x equals 0. I have the x-intercept at 1, 0. I have our key point at 2, 1. Then I also graphed 4, 2 and 8, 3. The graph of f of x's log base 2 of x minus 3 will be a transformation of our current graph, but we'll move it 3 to the right. Let's first think about the domain of the log base 2 of x minus 3. Because we can only take the log of positive values, we want to start by setting x minus 3 greater than 0. This says x will be greater than 3, which tells us our vertical asymptote will be at the line x equals 3. Now that we've moved our asymptote 3 to the right, we can also move our point 3 to the right and then connect the dots. Now we can see that our domain is 3 to infinity and our range is still -infinity to infinity. Let's graph f of x is the log base 6 of x plus 1 plus 3. We can see we have two transformations. We have a horizontal transformation to the left one, and then we have a vertical transformation up 3. The horizontal transformation to the left one tells me my vertical asymptote is now at x equals -1. This also tells me the domain is -1 to infinity. The range will still be -infinity to infinity. To start, I'll put in my vertical asymptote at x equals -1. If we think about the log base 6 of x, it would have an x-intercept at the point 1, 0. But now we'll move it to the left 1 and up 3. The log base 6 of x would also have a key point at 6, 1. Again, we'll move the point to the left 1 and up 3. Using these 2 points, we can draw in our curve of the function. Let's try one more. This time I have f of x is the natural log of 1 minus x. I'll start with the domain. I need to set 1 minus x greater than 0. This says -x is greater than -1. When I divide by a negative, I'll flip my inequality, which gives me x is less than 1. This time, my domain flipped to -infinity to 1. So we'll write in our domain is -infinity to 1, and that we have a vertical asymptote x equals 1. The range will still be -infinity to infinity. Let's put on our vertical asymptote at x equals 1 and talk about our transformations. We really have two transformations. If you look at the 1 minus x, we can rewrite that as -x plus 1. Then I'm going to factor out the negative to have negative quantity x minus 1. This says I have a horizontal transformation, 1 to the right, but I'm also going to flip the graph over the y-axis. If we look at the x-intercept of the natural log of x, we need to now move it 1 to the right, and then flip it over the y-axis. The key point for the natural log of x is at the point e1. Again, we need to move it 1 to the right, and then flip it over the y-axis. When we connect the dots, we have a graph that is decreasing and will follow the vertical asymptote x equals 1.